Hello everyone, welcome back to my channel Deep Understanding of Research Papers. In this tutorial I am going to explain a paper called Spoken Keyword Detection using Joint DTW-CNN. This paper is by Ravi Shankar, who is a PhD student at JHU, and C.M Vikram, research scholar in IIT Guwahati. Then S.R. Prasanna, he is a faculty member in IIT Dharwad. And in the overview of the tutorial is going to cover the paper overview, then we'll see what is the proposed method, then we'll see the dataset used for this particular experiments, and finally we'll see all the experiments and results. And in the overview, this paper is basically designed for keyword spotting. So many people may be knowing what is keyword spotting. So keyword spotting is about in an audio track, if you want to detect if there is a particular keyword, that is called keyword spotting. So for example, if there is a sentence, let's say Obama is becoming a new president, and my keywords are, let's say, president, and in that audio track I want to find out whether that the keyword president is present or not. So that is the problem of keyword spotting. It has a lot of useful applications, I mean, in many places. And in this paper they are using something called dynamic time warping in combination with the convolutional neural network to detect particular keywords in the audio tracks. And for this they combine, as I said, the algorithm they are trying to use is dynamic time warping along with the convolutional neural network. And the reason being, dynamic time warping is a very well known algorithm in dynamic programming, and also known as one pass dynamic programming. There are many variations, and these algorithms are very good at obtaining optimal sequence alignments. Given two sequence, it finds the optimal sequence alignments, and that is the algorithm is very well known for that, DTW. And CNN is, as we know, CNN convolutional neural network is a strong classifier for images. For example, it has achieved state of the art for object recognition in computer vision. And in this paper what they try to do is they take the DTW matrix. I will explain how the DTW matrix is constructed. So the DTW matrix is basically a matrix which will have at every location have the distance between 2 points in the sequences, two different sequences. Basically the distance between those 2 points, and using that local distance and along with some other things, you can construct that matrix for those two sequences, and you can feed that sequence, you can look at that matrix as some sort of you can look at that matrix as some sort of grayscale image, where you want to classify that particular grayscale image into 0 or 1, but depending on the presence of the keyword or absence of the keyword. And so as I said, the CNN is trained for these images to classify the presence or absence of the keywords, and the CNN has to somehow try to learn these textures of this warping matrices, which is basically the DTW matrix. I will explain you all that in detail. And for the data set, they have used timid corpus for all the experiments, and they show this method gives you better results compared to the old techniques, and I will give those results at the end of the slides. So in this proposed approach, they have three different parts. One is to extract the features. I'll explain what features explain extra on the other things. And most importantly, they are using the DTW, and they are doing some sort of modifications. I'll explain those, what are those modifications for that dynamic time warping algorithm. And at the end, they are using data augmentation, because the amount of data you need for training any CNN should be more, because otherwise the algorithm will not capture, the CNN will not capture, will not train very well. As we know, deep learning needs a lot of data, and for that they are doing some data augmentation, and at the end I'll show you CNN, which we all know. So in the feature extraction phase, what they use is they use something called Gaussian posterograms. So I'll explain what that is. Basically when you train any GMM model, particularly for example, if you look at this image here, this is one GMM model because it has multiple Gaussians in it, and this entire distribution you can think of it as summation over 4 different Gaussian models, basically, right? Means the number of the capital M number of components is basically 4, right? Because you have 4 Gaussians here. You can have 10, 20, 30, whatever number of Gaussians here. And what you could do is you can take the features which are basically the frequency ML frequency features, which are MFCC features. So they are saying 39 dimensional MFCC feature, and it's not 39, it's a 13 dimension, but they are using delta and double delta also, so it becomes 39 dimensional MFCC features. They take the data and they train a GMM using this 39 dimensional features. You can ask what are the labels. Since GMM is a unsupervised algorithm, you can train a GMM using a normal expectation maximization algorithm, and you will be able to fit a Gaussian to your data, which is speech data. So it's unsupervised training, right? So once you do that, so once you do that GMM training, what you could do is you can feed these 39 dimensional features and get these Gaussian posteriorograms. Basically, these Gaussian posteriorograms are nothing but the probability of each component given that particular feature. And if you have 10 Gaussian points, means if I have 10 number of components as 10, yeah, I mean basically these Gaussians are 10, then you will have 10 dimensional feature, because for every Gaussian you will find the probability. Just like here, you have a feature, you want to find out what is the probability of ith component Ci given the jth feature, which can compute it just using this way, which is Bayesian rule. You all know this, and this you can get it. Once you fit the GMM, you can get the likelihood, which is basically what is the probability of this data point given this particular component, ith component, and that way you will be able to find out this probability, which is a single number. So, and if I goes from 1 to m number of components, you can have 10 components, then you will get a 10 dimensional vector, which they call it a Gaussian posteriorograms, right? And they show and we'll see why they are using this. I mean, why means like they're saying this gives better than this gives better information than other feature methods, like other people whatever features they have used. So this Gaussian posteriorograms they are using, what they do is first they extract the 39 dimensional MSCC feature, they train the GMM model. Once they train the GMM model, they extract this posteriorograms, and it's very easy, as I just explained. It's simple. And once you get, for every frame, once you get the posterior feature, the posteriorograms, then you can do DTW. I'll come to that. So that is one thing. So that is the feature extraction method and GMM training method. And coming to the DTW, basically I'll explain the modified DTW before, and later I explain you like what was the actual DTW. So let's consider you have n posteriogram vectors for the reference audio. Basically, let's say you are given a audio track of 10 seconds and you are asked to find out a particular keyword in that audio track. So you have n number of posteriogram vectors, and that is called reference reference sequence. Then you have y1, y2, ym, which are m number of m number of posteriogram features for the keyword, which is called query here, and obviously m will be much lesser than n. And how do you construct the dynamic time warping, or how do you construct the warping matrix for these two sequences? This is sort of, you can think of this as sequence alignment problem, where you want to find out the alignment of the query in the reference. So if the alignment is really good, wherever the alignment is good, you will find a nice diagonal path, because whenever the alignment is there, wherever sequence alignment is there, you will find a less distance in that path, and that's basically the optimal path where the keyword is present, right? So, and you can use that information and feed it to CNN to predict whether the keyword is present or not. So we'll come to that, but before that, let's see how we are creating the warping matrix. So you put the reference reference sequence x1 to xn on the x-axis here, and you put the query sequence y1 to ym on y-axis, right? Now it's easy to then you can think of it as finding out the problem becomes like the problem finally it becomes like how do you find out the optimal how do you find out the optimal what is it optimal sequence alignment, so that you have so that you are able to predict the keyword. So simple. So what you can do is you construct this matrix by using these equations. I'll tell you first where these points, I mean this in the entire box, this particular, for example, box will have the distance value. Basically it's like how close the posterogram feature from y and x are. So I'll explain you what is that. So for example, if you look at d of 1 comma j, so j here represents 1 to n, which is nothing but this axis, and I represents the y axis, and you want to find out what is the values of the first row, right? So this is nothing but simply the distance of basically the distance, the local distance itself. So when I say local distance, you find out with x1 and y1 what is the distance. So the distance they compute is KL divergence, basically, because these are posterograms, which are basically the probability distributions, I mean vectors, probability vectors. So you can find out KL divergence to find out like how close the vectors are. So they are using KL divergence here. So, d of 1 comma j is the local distance of each box here that you can construct. Then this one is also you can compute the previous distance cumulated to the local distance from 2 to m, which is on the y axis. Rest is like this. So as you can see here, there are three equations here, and I will tell you what are these three equations. So first equation, for example, let's look at this location. In this location, if you want to find out the distance of this box or distance at this location, you can come in three different directions. One is this direction, another is diagonal direction, another is from bottom. So this one, a minus 1 comma b plus d comma a, could be like this one. So previous sorry, this one. So the previous distance, what you have your cumulated distance here, plus the local distance here, that is one number. Then you have one going from diagonal, which is this one, multiplied by the local distance itself, sorry, added to the local distance itself, that will give another number. Then finally you have another coming from left, which is a comma b minus 1 plus the local distance. So these are the three different numbers you get. Usually whenever we are optimizing whenever we are using this DTW or whatever one pass DP, where people will simply take the min of these three paths, right? It could be two paths also. Sometimes people will not consider this diagonal. You could simply take from I mean these two. So that way people basically take the min value out of these three, but here they are taking the mean value. Min is this, whichever is the minimum distance, but here they are taking the average of all these distance and they are using it. So basically this may be to smooth the matrix, I mean to get a smoother representation of the matrix, so that CNN finds it finds the alignment or finds the sequence, I mean the minimum distance sequence in very fast. So that way this is how the matrix is constructed. As I mean, I hope you guys have understood. One is distance is coming from here, another is coming from here, another is coming from here, and they're taking average of all the distances, and that is going to the local distance. Same thing happens to other points also. And as I said, this is modified DTW. In the old DTW, they used to simply take the path which gives you the minimum distance, and it was like single path. I mean, you can easily track it. Backtracking was very easy, but here it's an average of different paths, right? And as I said, you need data augmentation because the number of data points they are using is very less. I mean, number of data points in the sense, the amount of data you need for training any CNN is very high. So obviously we need large many images to train the CNN. So for that they are using some augmentation technique. So basically they have a random number generator. If the random numbers are between 0 and 0.33, they take the same equation and they add some noise to it. So noise is nothing but some number here. And in the same way they do, I mean if the random numbers are between different numbers, and they do this. So this is just for augmenting the data. And another augmentation they do is the DTW, the warping matrix looks like this basically, and they have done some flipping and circular shift to augment the current existing DTW data. And finally, coming to CNN architecture, they have convolutional neural network, trained convolutional neural network, which is similar to LayNet, which is the Jan LeCun's old CNN for handwritten recognition, with maybe two or three CNNs and one hidden layer. And that was the CNN used, and they are again using log likelihood, cross entropy as the loss function here, plus along with some L2 regularization, and that is the loss function. And obviously the training and all you may be knowing. I mean, training and all is, training the CNN is everybody knows these days. And so coming to the dataset, they are using timid dataset, and that is split into training and test. Already timid, when you download the data itself, you get training and test splits. And training as 4,320 speech files belongs to 432 speakers, and test as 1,680 utterances spoken by 160 speakers. And they are using 21 keywords with varying length chosen from the same timid database. I mean, you can ask, like, how did they get the keyword? Did they cut it manually? No, because phone level annotations are already done in timid. So you can simply go and extract that particular segment from that word for that word. Otherwise, you can use your own alignment tool, using some gentle or MFA something. Then there is using 7 templates randomly picked from keyword from the training set, and that is the data. And coming to experiments, they are using the same training speech files for GMM training, as I said, for training the GMMs to extract the posteriorgrams. And warping metrics are constructed for every test file, and for every keyword also. Combinations you can think of, like you have 100 files and you have 100 keyword, and you can get so many templates, warping matrices. And matrices are then converted into grayscale because you are feeding it to CNN. Once it converted to grayscale, they normalize all the dimension, all the audio files to 32 cross 128, but they are again broken into 4 pieces, non-overlapping pieces of 32 cross 32, and they label each one of them as the parent label. Basically, if the parent that 32 cross 128 is positive, all these patches will be positive. And they are using batch size of 1000. I don't know why, it's very huge, and the learning rate of 0.1. Then coming to the results, they have MTWV, which is maximum term weighted average score for keyword spotting. Many people use it. I mean, it's sort of wherever you read keyword spotting paper, you will see this maximum term weighted value as the metric for evaluating your keyword spotting algorithm. Here the better, as you know, here segmental DTW they don't have result. For non-segmental DTW they have 0.4, approximately 0.4, and using DN and HMM you get around 0.81, which is good. And if you go to CNN and varieties of CNN, like 0.84 is the one which you get once you use CNN 3, so maybe the better one. Then ER, I mean ER again, you must be knowing. So ER, if lower the better, and here also they show the for CNN3 this is lower, so that means this is sort of the best compared to all other existing keyword spottings algorithms. And that's it for this video. Thank you so much for watching this tutorial. If you are not subscribed to my channel, please subscribe for more video content. Thank you.